Okay. Okay, can you see the whole
Yes, I
screen,
can see
right?
the screen.
The
I can see.
presentation. Perfect. Okay. Okay, so thanks a lot. It's a pleasure to be here today giving this seminar. And as Antonio said, I will be discussing long-lived heavy neutral leptons at the LHC. Okay, so this is the outline of the talk. I will start with an introduction to heavy neutral leptons, or HNLs, and long-lived particles. Then we will move on to a slightly more theoretical scenario, which is effective field theories. We will introduce two theoretical frameworks in which we can describe HNL interactions in a model-independent way. And finally, we will discuss some of the related phenomenology at the LHC. Okay, so yeah, the discovery of neutrino oscillations just 25 years ago revolutionized our understanding of neutrino physics by proving that neutrinos have non-zero masses and exhibit a mixing pattern. So this breakthrough led to an extensive experimental program that has precisely measured these oscillation parameters. So these include two mass square differences and three mixing angles. So determining these two mass square differences confirms that at least two neutrinos are massive. However, we only know the absolute value of one of those mass splitting, so this leaves us with two potential mass orderings. So we have normal ordering and inverted. If this large mass splitting, known as the atmospheric mass splitting, is positive, then we talk about normal ordering, while if it is negative, then we have the inverted ordering. Current data shows a slight preference towards normal ordering, but it's only at the level of 2 sigma, so the question remains open. And besides this neutrino mass ordering, there are other mysteries in neutrino physics that remain. So, for example, we don't know the absolute mass scale, since the neutrino oscillation experiments are sensitive only to these mass differences. Then we also don't have a clue about the Dirac or Majorana nature of neutrinos. And in addition, we don't know which is the precise mechanism that gives neutrino mass. So this has been a thoroughly studied subject in the literature, but just let me review one of them. Okay, so first, let's see that in the standard model, in its minimal form, we cannot accommodate neutrino masses, because for writing, for example, this Dirac mass term, one would need a red-handed neutrino, which is not present in the standard model. And if we want to write this Majorana mass term using only the left-handed fields, then this would violate the standard model gauge invariance. So thus, to account for neutrino masses, we are sure that we must depart from the standard model. So the minimal renormalizable extension introduces these red-handed neutrinos, also called sterile neutrinos, because they are complete singlets under the standard model gauge group. And yeah, in this extension, one writes down this Yukawa type interaction between the lepton doublet, the red-handed neutrino, and the Higgs. So after spontaneous symmetry breaking, one obtains a Dirac mass, Dirac type mass for the light neutrinos, and to achieve masses of the order of 0.01 electron volts, which corresponds to this square root of the atmospheric mass splitting, then one should set the Yukawa to 10 to minus 13. So this is theoretically possible, but it's true that it might be unattractive to have Yukawa couplings spanning over 13 orders of magnitude, because, for example, the UCAVA of the top quark, it's order 1. So yeah, this is 10 to minus 13, might be not very attractive from the model point of view. So if we want to be a little bit more general, we can also write down a Majorana mass term for the right-handed neutrinos that, although violates lepton number, this is only an accidental symmetry in the standard model, so we are allowed to do that. So with these two terms being present, then after spontaneous symmetry breaking, the neutrino mass matrix takes on this form, which we have written just in one generation notation. It's just to get the basic idea. So one has to diagonalize this 2x2 matrix to obtain the neutrino mass eigenvalues. And we can do that also assuming some hierarchy between these two scales. So if we assume that the Dirac type mass is much smaller than this Majorana mass term, then the diagonalization leads to eigenvalues, one light neutrino state and one heavy neutrino state. And at leading order in this seesaw approximation, the heavy state mass is approximately the heavy scale MR, while the light neutrino masses are proportional to this UCAVA coupling squared divided by MR. So if this MR is very large, then one can naturally explain why the neutrino masses are so light. Now, also, if we want to reproduce the observed neutrino masses, and if we set the UCAVA to 1 as for the top quark, then one would require this M to be of the order of 10 to 14, 10 to 15 GeV. So these states in this case are completely out of range of collider experiments. But if one sets, for example, the UCAVA to 10 to minus 6, which is the case for the electron, then the scale of capital M drops down to 100 GeV. So in this case, these heavy neutrino states would become accessible to experimental tests. So they can also potentially provide some observable phenomena. Okay, so a byproduct of this diagonalization is that now the active neutrinos become a mixture of the light states and the heavy singlet states. And this neutrino mixing can be parameterized as follows. So one can decompose the mixing into two terms. This first term encodes, which is represented by the PMNS matrix, encodes the neutrino mixing parameters, which can be measured in the oscillation experiments. Whereas the active heavy or active astral neutrino mixing is parameterized by this phi, and this is model dependent. So in this type 1 seesaw mechanism and at leading order in the seesaw approximation, the squared mixing value takes this specific form. So here the right plot shows the predicted values for the square mixing as a function of MR for two different light neutrino values. So we can observe that it is quite small in this mass range, but the fact is that no matter how small it is, what we know now is that these heavy states, which were complete singlets, now they mix with the neutrinos and therefore interact with other standard model particles. So if these heavy states exist, how should we call them? Right-handed neutrinos, singlet fermions, astral neutrinos, heavy neutral leptons. So let me just introduce this concept of HNLs. Okay. So yeah, from an experimentalist perspective, a heavy neutral lepton is a neutral fermion that decays into some charged lepton plus W or charged lepton plus mesons, pions, and essentially it behaves like a heavier neutrino, but with a reduced coupling to the standard model charge and neutral currents. So this suppression is precisely parameterized by the mixing angle, which we know it must be small. Otherwise, HNLs with masses up to 1 TeV would have been detected. So when we refer to a heavy neutral lepton, what we mean is a neutral object with some reduced coupling to the gauge bosons. We are not specifying its mass. We are not fixing if it's Dirac or Majorana. And also at this point, we do not explain neutrino oscillation data. So to relate to this neutrino oscillation data, one should specify the CISO model, for example, the CISO variant. So then one might wonder about the utility of this HNL setup, right? So the thing is that this minimal framework is what experimentalists typically use to analyze the data. In this setup, you just have the mixing angle and the mass of the HNL. So this allows you to plot the discovery or the constraint limits on a mixing versus mass plane. So then the theorist can reinterpret these constraints within more elaborate models. So yeah, the simplicity of this framework, as I said, is that the production and the decay of the HNLs are entirely controlled by these two parameters. Since the mixing is expected to be tiny, the production cross sections are at colliders should be small, and as regards the decay, the small mixing angle suppresses the decay width. So this leads to large decay lengths, and in this plot, for example, we are plotting in this plane of square mixing versus HNL mass, and some diagonal lines fixed values of decay lengths. So this ranges from millimeters to even kilometers. So we see that in some part of the parameter space, these HNLs are potential long-lived particles. Okay, so for those who have not heard of LPs yet, these long-lived particles are basically particles that travel macroscopic distances before decaying, or that they even remain stable within collider sizes. And in the standard model, for example, we can already find some examples just to for instance, the muon, kaons, B mesons, all these particles have decay lengths of the order of meter. So they are observable within colliders, within detectors, I mean. But beyond the standard model scenarios, especially those involving weak scale physics, there are often LLP candidates. And these BSM scenarios lead to a rich phenomenology. They lead to exotic LLP signatures, such as displaced vertices, displaced leptons, displaced jets, even non-pointing photons. So these signatures are used in experimental searches looking for some new physics signals. So yeah, a lot of activity is ongoing in this direction at CERN, and is also expected to increase in the coming future. And the main experiments like Atlas, EMS are actively looking for LLPs through these dedicated searches. And also, huge interest in this topic has also led to several proposals for fire detector experiments, which are specifically designed for LLP searches. But before discussing some of them, let me comment on the role of the main detectors at the LHC. So yeah, their main advantage is that they cover nearly the entire solid angle around the interaction point. So they can see everything that's going on except the invisible particles. However, they face significant background noise, and this makes it challenging to identify rare events. So this challenge is what motivated the proposal of these fire detectors. So just let's review some of them. First is phaser, which is located in a service tunnel about 400 meters from the Atlas interaction point. So it searches for some neutral particles traveling along the beam line, and it is sensitive to decay lengths of up to half a kilometer. The main disadvantage is that it has a very small solid angle coverage, although it benefits from the boosted cross sections at the LHC. The good news are that the phaser was approved, it was built, and now it's already taking data in this round 3. Okay, the next one, the next proposal is called XP. This detector would be a cube-shaped detector placed in this empty space next in the LHCb cavern. It has larger solid angle coverage in comparison to phaser, but because it's at the LHCb point, it has lower luminosity in comparison to Atlas and CMS. So this means that there will be much less number of rare events. Now, next one is Mathieu's-Law. So this proposed large volume detector would be situated on the surface above CMS and around 100 meters away from the interaction point. It will also be shielded by all this rock between the main detector, between CMS and the detector itself. So this will allow, this will ensure that there will be zero background, at least in the upward direction. And if it is approved, this will be the largest of the experiments. And finally, once you comment about Anubis. So this was initially proposed to be placed in the axis shaft above Atlas. So this would feature some tracking stations, which could be provide a good sensitivity to LLPs. However, now a new configuration is being considered just to cover the ceiling of the cavern. So it's true that the solid angle coverage will be larger, but this being closer to the IP means that the backgrounds will also be larger. So yeah, they are still studying these issues. Okay, so we've seen that both the main detectors and the fire detector experiments are capable to detect these long-lived particles, and therefore they are also sensitive to long-lived heavy neutral leptons. So what is the current status, or which are the expectations for probing these HNLs? So this first plot shows the current exclusion bounds on this minimal scenario that is in the plane of the square mixing parameter versus the HNL mass. And the mass ranges from 1 MeV to 1 TeV. So these represent all different constraints from collider searches and also other type of experiments. For example, the high mass range, we see leading constraints from Atlas and CMS. here in the middle range, charm, Ne62, T2K, and for smaller masses, Bortzino and PNO. And yeah, looking ahead, if experiments like Phaser 2, the upgraded version of Phaser 2, or Methuselah, if they are constructed, the constraints on these HNLs will improve significantly. We can also see the sensitivity prospects for Dune and for SHIP. SHIP is a fixed target experiment that to be placed in the CERN SPS facility, and it was approved just 1-2 months ago. So yeah, good news as well. And yeah, what we can observe here is the complementarity between these far detector experiments with the main detector ones, so LHCb, Atlas, and CMS. Okay. So far we have discussed this minimal scenario where the only new physics beyond the standard model involves these heavy neutral leptons with non-zero couplings to standard model neutrinos. However, it is uncertain in some way if this scenario is realistic, right? New physics might be just around the corner. It's just that the LHC has not seen it yet. So if this is the case, the expectation of what the experiments will see might change. So in this part, we are going to introduce some theoretical framework to describe new additional HNL interactions in a generalized approach. Okay, so imagine any standard model extension that includes some heavy neutral leptons and other new particles with masses at a very high energy scale. So the most general approach to describe the effect of these new physics at low energies, that is the collider experiment energy scales, then the most general approach is using effective field theories. So these EFTs, they encapsulate BSM physics in these higher dimensional operators whose effects are suppressed by powers of a high energy scale called lambda. These operators represent interactions and contain only the light degrees of freedom of the theory. And each of them is accompanied by a Wilson coefficient. So as we grow, as we go to higher dimensions, we add more and more operators, and then also the number of parameters of the theory increases. However, one feature of these EFTs is that you can truncate this expansion at a certain dimension, because the higher the dimension of the operator, the greater is the suppression by these powers of lambda. So consequently, for larger dimensions, the effects become quickly relevant from a phenomenological perspective. So the framework in which one constructs all possible operators with standard model particles is known as the standard model effective field theory, SMEF, which has also been studied quite thoroughly in the literature. But today we are interested in this other framework, and our SMEF, which is the standard model effective field theory extended with right-handed neutrinos, somewhere around the electroweak scale. So this requires extending the list of operators to include those with right-handed neutrinos. And also significant progress has been made in the last decade. Now complete bases of operators up to dimension 9, I think, are known. And this other useful, there's another useful EFT when we study physics at some lower energies, as it is the case for meson decays. So this is called LEFT, the low energy effective theory of the standard model, or n left if we add these right-handed neutrinos. So in this case, the heavier degrees of freedom of the standard model, the top quark, the Higgs, and the weak gauge bosons, these are integrated out. They have to be removed, and one has again to construct the basis of operators containing only the light degrees of freedom. But we will revisit this later. Now let's focus on this NR SMEF. Okay, so in this theoretical framework, besides the right-handed neutrino kinetic and mass terms, we write down the higher dimension, all the higher dimensional operators contain this field, which respect the standard model gauge symmetry. So as I said, the most relevant operators, at least from the phenomenological point of view, are those of lower dimension. So we are interested in dimension 5, dimension 6, or even dimension 7 operators. Let's start with the dimension 5. So this first operator actually is from pure SMEF. This gives a contribution to Majorana mass for the left-handed neutrino. Then this second operator contributes to the Majorana mass term for the right-handed neutrino. And the last one generates a magnetic moment for the right-handed neutrino. We will discuss this third operator later as well. Then moving to dimension 6, we find several operator structures which can be classified according to their field content. For example, in this category, and the operators in this first column, these can generate active to astral neutrino magnetic moments after electroweak symmetry breaking. We will also come back to them later. The other main category at dimension 6 is that made of 4 fermion operators. So these operators can be divided into 2 groups, those containing 2 right-handed neutrinos, the per n operators, and those containing just 1 right-handed neutrino, or the single n operators. And lastly, we also have some lepton and baryon number violating operators. But anyway, we are going to focus only on these highlighted operators, since they can have an impact on the LHC phenomenology. Okay, so great. Okay, so let's start with for fermion operators in SMEF. Let's discuss first the single n operators. So these can contribute to HNL production at the LHC. In proton-proton collisions, for example, they can generate charged lepton plus HNL. And the production cross-section is proportional to this quantity. As I said, these are for fermion operators, dimension 6, so they are accompanied by Wilson coefficient divided by lambda square. And since the cross-section is proportional to the square of this quantity, then we find 4 powers of lambda. So in this right plot, we can see the different contributions of the operators to this production cross-section as a function of the HNL mass. And we have also included the expected contribution from the mixing for 2 different square mixing values. And yeah, I didn't say it, but we also have fixed lambda to 5 TeV. So you see that depending on which mixing value or lambda value is chosen, the contributions from either the operators or the mixing will dominate. And finally, I just want to add one comment, and this is that these fields in the operators carry a flavor index. So the Wilson coefficients are indeed matrices that expand in flavor space. So that's why we see here some four different indices. So for example, in this last operator, this charge lepton can be either an electron, a muon, or tau. Okay, so one feature of these single lane operators is that in addition to production, they can also trigger the HNL decay. So the HNL can decay back to a charged lepton and some quarks or jets, and the corresponding decay width is inversely proportional to 4 powers of lambda. So if this quantity is small, this will result in large decay lengths. So this could lead to some displaced vertex at colliders. Besides, because these operators have produced an associated charged lepton in the production, then there is an accompanying prompt charged lepton. So this signature, displaced vertex plus prompt charged lepton, can be looked for at ATLAS and CMS. So these experiments are sensitive to this type of scenarios. So one can estimate the number of expected signal events at ATLAS by computing the cross-section and computing these branching ratios, and also simulating what is the detection efficiency. So these are the results of the simulation, the sensitivity prospects in the plane of lambda versus HNL mass. Here we consider just one operator at a time and fix its corresponding Wilson coefficient to 1. So these curves represent 3 signal event curves, and in this case, the HNL couples to first generation quarks and the electron, and in the right plot to first generation quarks and tau. We can observe that the sensitivity is slightly worse in the tau scenario, precisely because the reconstruction of taus is more difficult than that for the electron case. But in both the scenarios, we can see that these kind of searches, displaced vertex plus prompt charged lepton, can be sensitive to new physics scales up to 10-20 TeV, and for a mass range of the HNL between 5 and 50 GeV, more or less. Okay. Okay. Now we move on to the per n operators. This here I'm displaying these 3 operators containing a pair of quarks and a pair of HNLs, so they can enhance also the HNL production at the LHC. And again, the cross section is proportional to lambda inversely proportional to lambda to the 4th. And now here we are plotting the contribution to the production cross section as a function of the HNL mass, and we see how it stays relatively flat up to some relatively large values of the HNL mass. So this means that we will be able to produce large quantities of HNLs up to some relatively large mass. Okay, but now the difference with respect to the single lane operators is that if we consider only one HNL, this cannot decay through the per n operators because of kinematic reasons, of course. So instead, one can refer to the mixing. So now the mixing is responsible for the HNL decay, so that the decay width is suppressed by the squared mixing value. And again, if one has very small mixing values, this will result in large decay lengths. So what we are doing here is decoupling the production and decay mechanisms, so we can maintain high rates of production while exploring very small mixing parameters. So now what we see is that far detectors at the LHC, which can be sensitive to decay lengths of the order of 1 to 100 meters, could be sensitive to these scenarios. So now we can again perform simulations to estimate the number of signal events reaching the far detectors in terms of the parameters of the model, which in this case are the HNL mass, the Wilson coefficient and lambda, and the neutrino mixing. So we can plot the sensitivity prospects in this plane, square mixing value versus HNL mass, if we fix the production coefficients. So here we are considering 3 operators at a time, and the lambda scale has been fixed to 2 TeV. So yeah, you can see how the probe parameter space reaches above 1 TeV, and also square mixing values as small as 10 to minus 22 could be probed by Atlas. It's true that we have fixed lambda to TeV, but if we change it to 7 TeV, this still looks quite promising. So very small mixing angles could be explored. Okay. Now we change a little bit the topic. Now we move on to asteroid neutrino magnetic moments, which has also received some attention recently. So the effective operators in and left that account for these interactions at low energies between the asteroid neutrinos and photons are given by these 2 terms. So these are actually the only 2-dimension 5 operators we find in the theory. The former represents this transition magnetic moment between 2 different asteroid neutrinos, while the latter represents the active asteroid neutrino magnetic moment. One notices that this first operator is antisymmetric under the exchange of the right-handed neutrinos. So this coupling in front is also antisymmetric. What this means is that in the presence of only one right-handed neutrino, this operator vanishes. So we require at least 2 asteroid neutrinos. Now, these 2 operators arise from operators above the electroweak scale in the NR SMAP, and in particular from these 3 terms. So this first operator, which is a dimension 5 operator, generates at lower energies this term, while these other 2 operators will generate the active asteroid neutrino magnetic moment. So one can relate the coefficients of the 2 theories by performing the matching procedure. But for illustrative purposes, and because I don't have a lot of time now, I'm going to discuss a scenario where only this first operator is taken into account. Okay, so this first operator, when we consider, or in the context of high energy collider processes, it is convenient to define a basis of rotated NR SMEF operators at the electroweak symmetry breaking scale, so that in the broken phase, besides this interaction term with the photon, we can also write this additional operator involving the set strength field tensor. So the latter is not present in the usual end left because the set is integrated out. However, it is convenient to use it here near the set pole because it describes the production and the decay of the astral neutrinos via this dipole-like coupling to the set pole. So this diagram here on the left depicts these possible production modes for of a pair of astral neutrinos in proton-proton collisions through this operator. And on the right, we can see the relative contributions of the two channels to the cross-section at the LHC for this center of mass energy. Again, we are plotting against the sum of the astral neutrino masses. And this solid line represents the sum of the two contributions. So we see that the set channel dominates when the masses lie below the set mass, but above that limit, then the photon exchange dominates the production. And as regards the decay of the astral neutrinos, this operator, as it is a per n operator, it only allows the heavier n to decay. So the n2, which is the heavier one, can decay to n1 plus a photon or plus a set. However, if we consider two heavy neutrinos with very similar masses, then there's not enough space to produce the set. So we will restrict ourselves for simplicity now in this case to this decay mode only, the one to the photon channel. Okay, so the decay width of N2 now is proportional to, or depends on this dipole coupling, the heavier neutrino mass, and this mass splitting that we have defined in this way. So small mass splittings correspond to the case where the two states are nearly degenerate. So if one has one of all of the three parameters very small, then one has suppressed decay widths and therefore large decay lengths. So in this scenario, the N2 is the long-lived particle candidate. And the potential signature, in this case at colliders, is a non-pointing photon. What we mean by non-pointing is that, for example, when it is produced in the decay of an LLP, which occurs at a secondary vertex displaced from the main interaction point, then this causes the photon to point away from the primary vertex. So if one reconstructs the photon trajectory, then one can determine which is the displacement with respect to this main interaction point. So this photon trajectory can be reconstructed precisely at the ATLAS or CMS calorimeter, electromagnetic calorimeters, and then one can use this signature to look for LLPs. So again, we in our work we discuss how an unpointing photon search can be sensitive to this scenario. So we estimated the number of signal events at the LHC detectors by computing this production cross-section, this branching ratio, and the detection efficiency factor, which again accounts also for the geometry acceptance. Yeah, these are our sensitivity prospects for ATLAS after the high LUMI phase. We are showing in solid and dashed lines 3 and 30 signal events respectively. And these are shown in the plane of the dipole versus the HNL mass. So here we have fixed the mass splitting. I recall that this is how it is defined. So we have fixed it to different values. And yeah, we see how this kind of search can be sensitive to these SRL neutrinos in this mass range from 1 GeV to 10, 15 GeV. And the sensitivity in the dipole coupling also can be improved, for it's below more than 1 order of magnitude with respect to the current constraint in LEP. Okay, so this is also quite of a simplified scenario where only one operator was considered. But if we allow for additional interactions, then a plethora of signatures emerge. So in this table, we are classifying different scenarios according to which interaction is dominating the production and the decay of the SRL neutrinos. So this has to be understood in the following way. The scenarios in the same row all share the same production mechanism, the leading production mechanism, while the scenarios in the same column, they all share the main decay channels. So for example, the scenario we just considered is this first one. But for example, in this second entry, we allow the lighter SRL neutrino to decay via this other operator. So the potential signature colliders here is consists of 3 photons, which can be potentially non-pointing. So analogously, other interesting signatures appear in the remaining scenarios, and it is worth exploring the capabilities of the LHC for probing all of them. And in our work, we comment on this in detail and also study numerically this second and third scenario. And if I have time, which I think I have, I want to comment on this final part, which is the case when HNLs are producing in meson decays. So here we are interested in a lower mass range for HNLs, namely sub-GeV-scale, so they can be produced in B meson, D meson, or even K-on decays. Okay, so then, as I mentioned before, the appropriate framework to describe the physics at these energy scales is NR left. So here we have to remove the top quark, the Higgs, the gauge bosons, and only the light quarks and leptons remain. So the basis of operator completely changes and new operator structures appear. So we do have lepton number violating operators already at dimension 6. So in our work here, we were interested in studying 4 fermion operators containing 2 right-handed neutrinos and also a pair of quarks, because these can trigger the decays of the mesons into 2-body and 3-body final states. And also here I'm showing the number of mesons produced at the LHC for this for 3 inverse octoparams of luminosity. So you see a huge numbers. So these are 10 to 15 number of mesons, 10 to 16 for the D mesons. So what this means is that with this large amount of mesons, we can explore very rare meson decays, which correspond to very small branching ratios. So what we did was first to compute the branching ratio of these rare meson decays, which can be triggered by these different operators. So in this case, we have selected this one, and for this flavor index combination. So we have fixed the corresponding Wilson coefficient to this amount, and we observe branching ratios of the order of 10 to -5, 10 to -6. So with 10 to 15 mesons, as I said, we could even explore branching ratios as small as 10 to -11, 10 to -12. So this would help constraining these coefficients a lot. So here as I said, this is the lepton number conserving operator, and just for comparison purposes, I'm showing you the case of a lepton number violating operator. There's this difference for smaller masses. This suppression for the LNC appears, because of some helicity suppression. And yeah, as I mentioned before, for the other N-SMEF operators, here we can study the production through Mason decays, but because they are per N operators, they cannot produce the HNL decay. So for that, we need the mixing. So again, one can compute the number of expected signal events at the far detectors in terms of the model parameters, and show the results in some of the planes. So in this case, we are showing the sensitivity results, which are the 3 signal events in the plane of square mixing value versus HNL mass, and we have fixed this operator. So this triggers B meson decays. These are the sensitivities for all these experiments. And one can turn the things around and fix the mixing parameter, and then show the sensitivity curves in the plane of the Wilson coefficient versus HNL mass. And then these small values of the coefficients can be translated into new physics scale in some way. So this reduces to 100 or even 300 TeV. So as you see, having such large amount of mesons allows to explore very high energy physics scales. And yeah, the other case, this other operator, which has a scalar structure, shows very similar results. The only difference is that when translating these coefficients into lambda physics scales, there is an additional power of lambda. So this translates into a 1 order of magnitude less sensitivity for lambda. But yeah, this is all I wanted to comment. So as I said at the beginning, neutrino masses cannot be explained within the standard model. So this might suggest the existence of heavy neutral leptons. And if these exist and they are at the electroweak scale, they are expected to be long-lived. So they are prime candidates for detection through LLP searches in these collider experiments. So besides that, there is a growing interest in searching for long-lived particles in general at the LHC, using both main detectors and also all these far detector proposals, such as Phaser, Codex B, Matthewsla, etc. So all these efforts have the potential to either discover new particles or significantly improve existing limits. So yeah, this would enhance in any case our understanding of physics beyond the standard model. Yeah, that's all. Thanks a lot for the attention.
Thank you very much, Rebecca, for the very nice and very complete talk. Question from the audience?
Yes, I have a question.
Yeah.
Rebecca, very nice talk.
Thanks.
To ask you, let me see, on page 23.
Okay.
The production there. 20,
yeah.
Yes, here. So you have this this cross section of PP to production of N, and it has a big drop there at a mass of like a little bit below 100 GeV. Why is that?
Yeah. Okay. So this gray line corresponds to the mixing contribution. So the mixing production mechanism is through W gauge boson. So when when the HNL has a mass larger than the W, then it cannot proceed through on-shell diagrams. So there's only the off-shell contribution is present, and that's why you see this sudden drop precisely at this 80 GeV.
Right. Okay. Yeah. Thanks.
Yeah.
More questions? Rebecca, you had a question in... Yes,
I have a question. Sorry, Antonio. Well, thank you for the presentation. Very, very nice. Can you go to this to the part of the photon signal?
Yes.
That appears from the decay of the heavier. Yes.
Yes.
So my question is it seems that all the studies or the searches for this type of signals are below, let's say, 100 GeVs for the heavy neutron leptons. Yeah. What about the heavier, for heavier masses around, above 100 GeVs, for instance? Is it possible to search for those type of signals?
With non-pointing photons, yeah. The thing. So what happens is that the decay width, which ultimately determines the decay length, is proportional to the 3 powers of the mass. So if you go to very high masses, then you have very small decay lengths. So you lose the display signature, let's say. Yes. I mean, yeah. So if the HNL mass, this heavier neutrino, is around 1 GeV, then the decay length is expected to be less than 1 millimeter or less than 10 to minus 6 meters, for example. So you cannot distinguish if this photon is pointing back to the primary vertex or not. So there are a lot of photons. There is a lot of background photons. So this is the only way to distinguish.
But at the same time, you have this D and gamma coupling that you can decrease in such a way to compensate that effect.
Exactly. It's a trade-off, right? So if you increase the mass, you can explore smaller coupling values. The thing is that in this case, this coupling is also responsible for the production. So if the production coupling is very small, you don't produce enough events. This is signal. Exactly. So this is what happens when you have only one coupling controlling both the production and decay. Only in the case when you decouple that, you can play more with the couplings.
Okay, but this is can we say that it's a model dependent effect, that the production and the decay is dependent on a single parameter? Well, this is an effective field theory.
Yeah. So actually, what we do here is just consider one operator and consider the contributions from other operators or other interactions negligible. For example, in this scenario, we computed which was the mixing parameter that would make its contribution to be subdominant to production and decay. So these scenarios are only valid in some part of the parameter space, of course. Yeah.
Okay. Just for curiosity, so beyond this heaviest stereo neutrinos framework with this type of signals, have you seen some experimental searches for this type of photon decays or photon signals coming from a heavier or
Yes.
from a long-lived particle, but in the heavy mass range?
I mean, I know there's some searches at Atlas and CMS looking for delayed and non-pointing photons, and they actually look, so the theoretical framework that they consider, I think it's in SUSY, so they have, I think they have a neutralino decaying, which is the long-lived particle candidate. I think in this case, the mass range is larger. So yeah, they are sensitive to larger masses, but because it's a completely different framework. So yeah, there are some recent searches looking at this.
All right. Okay, thank you very much.
Thanks.
More questions? Rebecca, I had one question. In the part in which you analyzed the discovery sensitivity for these heavy neutral leptons, when you show several operators, you mentioned that you were considering in the contribution the first family of quarks. I am wondering how your results will get affected. For example, if you also consider, let's say, second family of quarks, because, for example, for the PPG, the strength, of course, the correction is subleading, but maybe it will correct some percentage or your results regarding the will be very unaffected. For example,
you mean second generation quarks, right?
For example, second for the down. Maybe for the up,
Yes.
I see in the PDF for the chart will be very small, but maybe the PDF for the strength, for example.
Yeah, so we actually look at that, and we also simulated those cases, and I think the sensitivities were slightly worse, but they were not much affected. Yeah, as you said, this is related to the PDF of the proton, so of this second generation quarks in the proton, but yeah, there were not so much differences with respect to this first scenario.
I see. I see. And for the other operator in the slide which you were discussing with Bastian, the operator that was having the C, how you explored also the signal, for example, instead of yes, this slide, they came, for example, the similar diagram like this one, but with the C gauge boson in another mass regime, for example, let's say around 200.
Yeah, so actually, okay, so this, as I said, in this case, we were considering only this operator, so this was the final signature. But in this other scenario, we consider two different mass regimes for N2 and N1. So the N2 was heavier, and it could decay to the Z boson. So we allowed for the N2 to decay to the Z boson. But because there are a lot of Zs and Ws produced at the LHC, this would be very difficult to distinguish from standard model processes. So that's why we restricted ourselves to the photon case. I mean, in here, we consider it in the computation width of the decay width, but we do not include it as a final signal state.
I see, because this other process has a very large background, very large standard model background.
Exactly,
much larger
exactly.
Than the process that you are considering with the photon in the final state with the N1.
Exactly, which is non-pointing, exactly, and can be distinguished more easily from the backgrounds, from other standard model processes, exactly. But we do consider it here, the decay into the Z boson, for example, or in these other scenarios. So we do take it into account.
Thank you very much, Rebecca. More questions from the audience?
Thanks.
If there are no more questions, we thank Rebecca for the very nice, very excellent, very complete talk. Thank you so much, Rebecca, for the very nice talk.
Yeah, thanks. Thanks a lot.
And we meet at the next seminar. Have a nice time, all of you. Thank you so much.
Okay, thanks. Bye. Bye to all.
Bye.
Thank you,
Bye.
Rebecca.
Bye.
Thank you.
Bye. Bye.